I go on where I was left off. Okay, so thanks everybody for coming back, and today I'm going to talk about an application. There was one thing I forgot to say yesterday, and that is actually an important remark. You could say, why does large deviation work? Why does it have such a nice structure? And the reason is that since large deviations is about extreme events, if a process, random process, tries to do something extreme, it will do it in what we call the least unlikely of all the unlikely ways. So it is doing something optimal. And it is this optimality that brings a lot of structure into the theory. And that is also why you see variational principles around. And that is really the reason why it works. If you do something extreme, you will not just do it in a silly way, you do it in a very structural way. And that structure is what large deviation is trying to capture. Okay, I'm going into one application here, and it's the following. I want to consider two independent random walks on the d-dimensional integer lattice, both starting at the origin, and these random walks can have arbitrary transition kernels, but I'm assuming that the transition kernels are symmetric, so a step in one direction must have the same probability as a step in the other direction, but any step is allowed. So this may be simple random walk, which only steps between neighboring sites, but it could be anything else. And I'm going to be interested in what is called the total collision local time of these random walks. So I'm summing over all moments of time, and remember that n0 are the integers starting with 0 of the indicator that these two walks meet. It doesn't matter where they meet, but what's important is that they meet. And what this v is the total number of times that they have met each other over an infinite time interval. Now, it is easy to see that if this transition kernel is the kernel of a transient random walk, and transient random walks are abundant in dimension 3 or higher, but they can also occur in dimension 1 and 2, then this number is finite with probability 1. So it starts to make sense to study the large deviations of this object. I should also say that if the transition kernel is recurrent, then this number is infinity with probability 1, and there isn't really anything interesting that we can study. And this is a simple computation. If you compute the expected value, okay, I have to get another piece of chalk. If you want to compute the expected value of this number, then this becomes the sum over all k in n0 of the probability that they meet, and that is the same thing as the 2kth power at the origin of the transition kernel, because I have to say here that by symmetry, the probability that sk is equal to s prime k is exactly equal to this number, because I am using this relation is the kernel iterated twice and then looked at the origin. And it's from this formula that you see that if you have a recurrent random walk, then this is a finite sum. And if you're an expectation finite, you must be finite with probability 1. And if your recurrent, this sum is infinite, you have an infinite mean, but you can then easily prove that actually you are infinite with probability 1. So I want to restrict myself to transient random walks and ask myself, can I say something more about this number? And So here's a picture of what such a collision local time is. You have two random walks starting at the origin. Here is one path, and this is space, and this is ZD. I've drawn it just for one dimension, but you should imagine that this could be, that this is actually the d-dimensional entity of time. And you follow this path and you say, how often do you collide? And this would mean that up to this time there have been 5, well actually here also since you start at the same point you actually have 6 collisions up to that time here. And when you're transient, these random walks will eventually go off into different directions, and this number of black points is finite. And I want to understand the distribution of the number of these black points. Okay? So the question is very simple. Now, what are we going to do? We're going to do the following. I'm going to look at I'm going to take a number z, which is non-negative, and I'm going to take the expectation of z to the power v. So this is a kind of moment generating function of this random variable v, where if I would replace z by e to the something, okay? And I'm asking how big can I make this number z before this expectation explodes? And that number I will call z2. And so for instance, you immediately see that z2 has to be larger than or equal to larger than equal to 1, because if z is smaller than 1, this number is certainly finite because v is positive. But it could be that v has an exponential tail. It's hard for two random walks to create very many self-intersections, and then this z2 would be a number larger than 1. And at this moment I don't know what this number is. I cannot easily compute it. We will see it later, but I want to define it. And at the same time I want to define something completely similar when, however, I freeze one of the walks. So this is the question now: freeze one of the walks, ask what the expected value, what the moment generating function is of this v when you average only over the other walk. So there's a difference between these two. Here I'm only taking an expectation over s prime, the second walk, but keeping the first walk as fixed. And here I'm taking the expectation over both. And it is completely clear that because this thing is the expectation over s of that thing, that this thing is really typically bigger than that, and therefore z2 can never be bigger than z1. It's less than or equal to z1. Okay, and my question is, when is it the case that they're not the same? And when they're not the same, something interesting is happening, because you can think of these quantities here as meaning the following. I have my two random walks and they are independent, and now I say each time you meet each other you get a reward, and the reward is a number z. And if z is larger than 1, it would mean yes, you would get the two paths get a reward in probability when they meet, and each time they meet they will get a reward z. And so these numbers are actually describing a model where you say you have two paths, they are not independent, but every pair of paths gets an extra bias weight, which is given by z to the power of the number of intersections. So if z is very, very big, the paths are very happy to meet many, many times, and you see that under that bias law they are just going to run around each other and trying to keep on meeting each other a lot. Whereas if z is very small, they will not be interested in doing that. So these numbers in a way are the critical thresholds for when the two walks like to stay close to each other or not. Right? And you can think of this as what we call in physics the quenched version of the problem, where one walk is fixed and the other is free. and this is the annealed version of the two walks where they are both running. And if there is really a gap, then that means that it is for the second walk much harder to intersect with a frozen walk than with a non-frozen walk. So if I freeze one walk and I say to the other, try to intersect this guy as much as possible, then if there is a gap, then that would be harder to do than if I say the other guy may also come into the play and try to look for you. Right? So if there is a gap, then something really interesting is happening. Freezing one walk makes it really substantially more difficult for the other walk to have intersections. Now, we're going to assume that my transition kernel is nice. We want this number here, the probability that you return to the origin after 2n steps. I would like this to be regularly varying at infinity. There are some other conditions actually that we need, which are true for all walks that I can imagine, and I actually claim that they're true for all walks. But they're a bit technical, I'm not writing them. There's some kind of regularity property, which is probably true for every walk, but we cannot do it. And here's the theorem that says there is a gap whenever this sum is finite. And this random walks which have this property, we call them strongly transient. They are random walks with the property that they are so transient that if I condition on them coming back to the origin, they will do it in a finite time, on the average. Okay, now there is a conjecture that actually we don't need this n, and that the gap is true whenever I have a transient random walk, and since I already know that this gap is not true whenever a recurrent random walk, this is very easy, because for a recurrent random walk, these numbers are both equal to 1. Right? Because if z is less than or equal to 1, this is not exploding, and when z is larger than 1, it explodes, because this number is infinity. So the recurrent case is not interesting. Z1 is equal to Z2 is equal to 1, but we believe that for transient random walk there is a gap, but we can really only prove it when under a stronger condition, which is called strong transient. Now, and this is an interesting phenomenon. It's interesting because the presence of this gap has an immediate implication for the occurrence of some interesting phase transition in 3 different models. There are models of particles that branch and that move around. And I don't have time to really go into the details of what these models are, but there is a model of branching migrating particles. There's a model of diffusions that are labeled by the lattice and that are interacting, and there's a model about copolymers. Copolymers mean random polymers interacting with an interface, and in each of these 3 models there is a certain key quantity that can be exactly captured by these 2 numbers, and the fact that there would be a gap between these numbers would imply that these 3 models have some very interesting phase transition. And now it would take me another afternoon to explain this to you, but I'm only using this to tell you that this gap problem actually has a deeper meaning in several other models, and that's why we came to study it. We studied it not because we thought of it by ourselves, but we were actually working on these models and realized that they had something in common, and that this gap was somehow a key thing to study. So we will be trying to prove this theorem here. Now, in order to do that, I am going to apply large deviations. And the idea is that if I look back at this picture here, that I'm going to think of all the increments in this piece of the path as, you know, a sequence of letters, in this case letters up and down, and I'm going to do that for all the pieces in between when they meet, and I'm going to read the increments, the sequence of increments, as a kind of random word. So this sequence here is a sequence of increments, and I want to read the increments in between the collisions as words that have a random length and a random letters, and the letters would be the increments. And once I know that, I will be able to come back to this picture and solve and prove this theorem. Okay, so what we're now going to do is we're going to forget for a moment about this random walk. We will be coming back to it at the end. And I'm going to look at a problem that involves letters and words and sentences and large deviations of those. Okay, so that's the goal that we're going to do. And what I'm going to describe are two large deviation principles. And this is work I did a while ago with Matthias Birkner from Mainz and Andreas Greven from Erlangen. Okay, and the description of the problem is not complicated, and as I said, later we will see how this can all be fit into this random walk problem, but we forget for the moment what the random walk problem is. And I'm going to do something very simple. I'm going to start by drawing an IID sequence of letters, which I label, the kth letter is xk, and they can be drawn from any countable alphabet. This alphabet could be consisting of the number 0 or 1, or it could be consisting of all the integers, or it could be consisting of all the vectors in ZD. It is some countable alphabet about which I do not need to assume too much at this point. And I'm going to assume that the letters are drawn independently according to some probability distribution on this alphabet, which I denote by nu. Okay, and then what I'm going to do is I'm also going to draw a sequence of times, an IID sequence of times, which I call renewal times, and they are drawn from the positive integers according to some law rho. So let me write that down, because these things are going to come back more often. I'm having so these are ID E-valued letters with law nu, and then I have tau is tau E. They are ID n-valued times with law rho, and these are important choices that we can make. You can, for the moment, make any choice that you like. And then what I'm going to do is I'm going to define a sequence of times which are just the successive sums of these times. So t0 is 0, and for every I, ti means the sum of all the first I tau i's. There's a plus sign missing here. And then I'm going to introduce something that I call the ith word. The ith word is just going to look at what this sequence looks like between time ti minus 1 plus 1 until time t. So it says, so basically there is a picture here, and let me put that picture in as well. I am having here time. I'm having here my letter sequence, sorry. So there are letters here at these points. And now what I do is that I make a lapse of length tau 1, and I'm looking at, so this is time 0, and I'm looking at the word that I see here, and this I would call the first word. And the first word is just all the letters that I see during the first time lapse. And then I'm going to make another time lapse, which will have length 2, and I'm going to look at all the letters that I see in that next time interval. And I would call this y2. And I continue doing that. So out of this, I construct a sequence which is I, yi, where I runs over n. And this is the sequence of words cut out from x by tau. And you could think of this thing, if you wish, as an infinite sentence. Just an infinite sequence of words. Okay, so that is the object that I'm building. And here is this picture again, which I have on the blackboard. So it's very simple. You give yourself a realization of this sequence of letters, and now you jump forward always by these random times, and each time you look at what you have jumped over, and that gives you a random word, and the word has a random length and a random content. Okay, and I'm interested in the sequence that I see here. So what does this random variable live on? It lives in the sentence space, where first of all there is a word space, which I call twiddle, and this is just all finite words drawn from the alphabet, which is written here. And then I can continue doing that, and this twiddle space to the power of the integers will be my infinite sentence space, and this process takes values in this space of infinite sentences. Okay, so the setup is very simple, very basic, and I'm going to be interested in the large deviations of this sequence. So this large deviations of this sequence of words. Okay, so the way we're going to do that is we're going to build the empirical process of these words. And remember what I was saying yesterday, how do you build that? You take the first capital N words, you periodize this to an infinite sequence where this is being repeated, and then you shift this sequence around n times, so that you just randomize over the beginning of which word you want to consider to be the first. And when you do that, you obtain an empirical process of length of size n. This is, by its very definition, a probability distribution on this sentence space, and it has the additional property that it is invariant under the left shift theta twiddle acting on this space of infinite sentences. And I've put it, yesterday I didn't have a twiddle, but now I have a twiddle because I'm looking at this space of words, right? And so that's a different space. Okay, now by the ergodic theorem, it is very easy to prove that this quantity has a weak limit. It will actually converge to the law of the whole word space, on the typical law. And what is that? Well, how do you construct the first word? Draw tau according to rho. The probability that the first word has length n is rho n. And then each letter was drawn independently in this sequence anyway. So what you will see under your word is a product measure, and this describes the probability distribution for a single word of any length and any symbols that you put in. And if I look at this problem here all together, where I'm looking at the joint law of the x and the tau, I will find that the first word simply has this easy distribution, and that and all the other words are independent because I have chosen these lengths independently and all the letters independently. So if I just say, what does the first word look like, I see the Q. If I say, what does the second word look like, then I would say it doesn't matter where this thing started. What I see is again a repetition of the same thing. So actually, under the joint law of these two things, this is just an ID sequence. It lives on a somewhat more fancy space because the words are living on a somewhat more fancy space, but otherwise it's just an ID sequence, and the ergodic theorem will tell you that this empirical process converges to this simple law, which is completely explicit. The moment you give me what rho is and what nu is, we are there. And for instance, here you could choose these things to be plus or minus 1/2, and maybe this could be any law that you like, and so the limiting behavior of this law is very simple. Okay, now what I'm interested in is the large deviations of this object away from its typical behavior. That's what I want to study. And later I will show that large deviation principle will be the key to understanding this behavior of these two walks that are intersecting. Okay, but that will only come towards the end. Okay, now since this is an ID sequence, there is a large deviation principle that is simple. It is the large deviation principle that we encountered yesterday. If you look at the probability distribution of this quantity under the joint law of the letters and the times, then this is just a large deviation principle for an ID sequence of random variables that lives in a slightly more fancy space, which is this word space, and therefore it will satisfy a large deviation principle in the weak topology with rate n, and with a rate function that is just the specific relative entropy of the measure that you want to be close to in this shift invariant infinite sequence space relative to your law, right? And so if you say, what is the probability that I'm doing something close to this easy limiting law, then that would be tending to 1, because then the relative entropy is 0. But if you want your empirical process to look very different from this ID sequence, then you have to pay, and what you have to pay is the specific relative entropy of Q with respect to this easy reference measure. And this is true for any Q that you choose on your infinite sentence space. And so this is a very big space of all shift invariant stationary distributions that also can describe very dependent processes Q, but the large deviation principle will tell you that this is the rate function. Okay, and this is an object that we have a description for. I was talking about this yesterday. Now, this rate function is lower semi-continuous. It has compact level sets. It's actually affine, and it has a unique zero which only appears when you want the Q to be the typical behavior. Okay, so that's easy. As long as we are interested in this thing under the joint law of x and tau, we have very classical stuff. There's nothing new under the sun. It gets more interesting if I'm going to do the following. I'm going to ask myself, can I also understand the large deviations of this empirical process when I freeze the letters and I only allow my jumps to come into the game? So what would happen if I would say the letters are no longer playing the game, they are frozen. I am now somebody who looks at a frozen sequence, which is there and is not changing, and I'm supposed to make jumps so that my empirical process of words is close to something that I would like to choose and call Q. Then the problem becomes really different and difficult, because if I jump, I see a certain word behind me, and I see a certain word before me. Now, if I would have made the jump a little longer, I would have seen something different here, and I would have seen something different there. And my letters are frozen. Before they were not frozen, so everything was random, and no matter how far I jumped, I would still see the same thing in probability distribution in front of me. But that's no longer the case when you freeze the letters. You say the letters is there, and so it starts to, whatever the probability distribution is of what I see in front of me, depends on how I was jumping. So the moment you freeze the letters, finding a large deviation principle becomes very difficult. Now, nevertheless, I can state a large deviation principle, and I need to define an additional object in order to do that. And that is not very difficult. Suppose, look at this. Here I have been cutting out of an infinite sequence of letters an infinite sequence of words. I could do a reverse operation. I could say, suppose you give me a couple of words, I can glue them one after the other, and I get a sequence of letters. So I can introduce a concatenation map, which is just the opposite of a cutting map, that says if you give me any sequence of words, I can put them one after the other, forget where every word started and ended, and I get an infinite sequence of letters, and I would call that a concatenation map from the sequence of words to the sequence of letters. Now that map is very simple. It's as simple as its opposite, where you are cutting words out of a letter. Now if you give me any probability distribution that is invariant under the word space, such that the words have a finite mean length, this is not always the case, but suppose it is, then I can define basically a distribution on this sequence of letters by concatenating the y. Now, if I would do that, if I concatenate words that I've drawn randomly, your first reaction would be, when you do that, you automatically get also a shift invariant letter sequence. So if I start with a stationary sequence of words and I can concatenate them, I get a letter sequence. Question: is this letter sequence automatically stationary? The answer is no. So what we're doing with this object here is we are making it stationary by randomizing over the beginning of the first word. That's the same thing as we were doing in the empirical process. It so happens that when you have a stationary distribution of words and you can concatenate them, you may end up with a stationary sequence of letters, or you may not. And this is a way to re-stationarize the sequence of letters by just shifting it over the beginning of the first, everywhere in the first word, and then taking the expectation and dividing by the mean. You get a probability distribution on sequence of letters induced from the probability distribution Q on the sequence of words by this concatenation map. And the only little drawback that you have is that you have to re-randomize the beginning of the first letter over the first word in order to make sure that you really get something stationary. Sometimes you don't have to do that, but in general you have to. So you have to think of this psi q as a probability measure that is shift invariant now on the sequence of letters that is induced by the concatenation map from the sequence of words. So I'm saying you are giving me a stationary sequence of words, whatever it is, glue them together, randomize the beginning a bit. What you get is a stationary sequence of letters, and the law of that stationary sequence of letters is psi q. That's all that you have to remember. If the mean word length is not finite, then unfortunately I cannot do this, but I can do it in an approximate sense by cutting the words when they become too long and then passing to a limit. We call this a truncation approximation. So I could decide that very long words above a certain length, I forget the rest of the word, but if the cutting length is very big, then this will give me a good approximation of what is actually going on. Okay, so with every q there is a psi q associated with it. Q lives on the sequence of words, and this lives on the sequence of letters. Now, here is the annealed, here's the quenched LDP. We're going to look at the empirical process conditioned on the letter sequence. So the letter sequence is frozen, and the statement is, for almost all choices of this letter sequence, and remember we drew the letter sequence according to this product measure nu, where nu was the one according to which I chose my letters from the alphabet. For almost all choices of x, this conditional large deviation principle, this conditional distribution for the empirical process satisfies an LDP with a certain rate function, which we will talk about in a second. I need to make an assumption. What I'm writing down is true for all choices of rho that are the following. Rho is n to the minus alpha plus little o of 1 as n goes to infinity, rho of n. So where alpha can be any parameter between 1 and infinity. So I'm assuming that these times have a polynomial tail with an exponent alpha. And the exponent can be anything you like. Okay. Under that condition, this conditional rate family satisfies a large deviation principle with rate n and with a rate function. First of all, this rate function turns out to be deterministic. It doesn't depend on x. So there is some averaging going on. Okay. And the rate function is very interesting. It is the old rate function that we saw in the problem where I was also averaging over this x so that the condition disappeared, plus something else, and the something else is this, how much this exponent differs from 1, the mean word length under q, plus again a specific relative entropy, but now at the level of the letters. This is the original letter distribution. This is the projection of q onto the letters, and I'm again having here a specific relative entropy of what the q projection would give on the letters compared to the reference law of the measures. Just like I had here the specific relative entropy of the entire q with respect to the entire typical value of q. And now my rate function is a sum of two parts. It's the old part that we already saw plus something new. And the something new is sort of living in the world of letters and asking for specific relative entropies of letters. And this only makes sense when q is such that this is finite, but if that's not the case, you can do a truncation approximation where you say I first truncate all the words and then I later pass to a limit. So that's okay, you can talk about that also. So what does this say? The first thing that it says is, yes, even if you condition on x, there is a large deviation principle. Good news. It also says the rate function is different. There is the old rate function plus something more. So, and the plus something more tells you that, well, this is typically, well, it could be 0, but it's typically sort of positive. So apparently it costs more to create a deviation on a fixed x than on when the x is allowed to take place in the game. So here, this is me, I'm walking on this frozen sequence. I say, I'd like to jump over this sequence and then create, I'd like to see a sequence of words that you prescribe me because you want to see a certain cue. And then I have to conclude that it is harder for me to do that when the sequence is frozen, and I have to do all the work. I have to go and find places where I can find the right words with the right frequency. Then when the sequence says, I'm free, I'm going to be able to give you a helping hand by occasionally in front of your nose looking like what you would like to see. And this thing is quantifying that. Now it is quite rare in large deviation theory that when you have a quenched and annealed problem that you can identify the rate functions. And it's also quite rare that you can actually see that the quenched is the annealed plus something very explicit. We very often know that the quenched rate function should be bigger, but we are very rarely able to quantify it, let alone that we could say it's really the annealed one plus something very explicit. So this result is sort of remarkable, and we were surprised to find it. Okay, now I'd like to draw a little picture, and this is the only picture that I will put in order to give you some feeling of why there is this extra term. Look, I'm this guy standing in front of this frozen sequence, and Siva has told me I would like you to produce, by walking on the sequence, an empirical process that looks like this, Q. Okay, so what can I do? I could say, if I create my first word here, that's going to be very hard for me to do that, to get something that Siva wants, because it doesn't look like what is there. But what I could do is I could say, let's look down the sequence. Aha, I see a wonderful spot over there that looks like what Siva wants to see in his third word. Let me make a huge jump and go there. And then I say, now I'm standing in front of something that really is looking in front of me, is a word that is very much the word that Siva wants. And so I'm now going to make a jump and create a word that Siva wants to see. Okay, and maybe I go to a spot where I say, look, I see in front of me already 10 words that Siva wants to see. So now I can cut and create 10 words, and that is fine. And I've said, okay, yeah, but you had to make one huge word that didn't look at all like what you want. But then I said, that's only one word. And if I take an empirical distribution, what is one word if most of the time I do the right thing? So the trick is that the way you create your large deviation is that you will look for spots in the medium where you can create with small steps a very large number of words that look like what Siva wants. And you can do that. You can look for pieces in the medium where you can do that. And then all you have to do is to make a very small number of big jumps to go to these regions. And as long as these regions are very much more in number than these few here, these few I will never really see in my empirical distribution because I'm doing a large deviation in the weak topology. Okay, so that is sort of the secret behind the large deviation principle. And what is happening is that in these pieces, I am essentially paying what I would see if the x's could play in the game, because I'm simply looking for stretches where the x is doing for me what I want. And the other term, the extra term here, comes from the fact that I do have to pay a price to move to the regions where I can do something nice. There will not be many such loops, so since they will be very few, I will not see them in the limit for the empirical distribution, but they have a serious cost, because a very long loop is very unlikely, and it's the cost that is captured by this object here, and that's also why this parameter alpha, which determines the cost, is appearing in here. So this is a part that I pay for doing large deviations on stretches that I found that cooperate with me, and this is the part that I have to pay to find these stretches. Okay, and that's it. That's all that is behind this. So, and this is typical for the quenched situation. If I would be in the annealed situation, I could simply create this long sequence in front of my nose and everything would be taking place here. But now in the quenched setting, I must find, I must look for good stretches and do it there. Now, you have to worry about lots of things here, but basically what we find is that the quenched wave function is the sum, very unusual, of the annealed wave function and an entropy term involving a certain tail exponent and a certain concatenation randomization. Right. And so we have been successful in finding the quenched wave function. I am not in a position to give you the full proof of this because it's really very complicated. We use ergodic theory, we use combinatoric large deviation theory, entropy estimates, compactification, modification arguments, projective limits. It's very difficult, surprisingly difficult, and it was a big struggle. It took us quite a long time to actually prove this theorem. But fortunately, something interesting came out, and what came out is also very explicit. Because what often happens if you do large deviation theory in some kind of random environment like we are doing here, where X is a random sequence, you often find that yes, there is a quenched wave function, and no, we're not able to compute it. We may be able to say a few nice things about it or prove that it's bigger than the annealed wave function, but it's actually quite rare that you can compute this. And here there is of course a very beautiful structure. There's you know, you're cutting this words out, and everything has a certain direction in which you cut, and the gluing is also a simple operation. So there is something simple about this model that still allows you to really get your hands on this whole rate function. Okay, the rate function is not particularly easy because these are specific relative entropies, and if Q is a very complicated thing, then psi Q is a very complicated thing, and these numbers are not easy to compute, but at least we have something in our hands. For most quenched models, you simply don't have anything except some kind of abstract thing.
Is it crucial that the two random walks are identically distributed?
No, I think if they would not be identically distributed, this measure would be different and that measure would be different. But in order to actually prove this theorem, we are making serious use of the fact that the letters are independent and that the words are independent, and it would require additional work to get away from that. I had a short paper with Julien Poisat in which we made the letter sequence be very mixing, so that you say they are not independent, but they are exponentially mixing, and then we could go through the steps of this proof and say, this is the same, that's the same, here you need to change your argument a bit, this is the same, that's the same, here you need to change your argument. So that we could do. And so certainly under strong mixing conditions you can make this work. And then these reference measures would become different, but they would still be very nice. And specific relative entropy is well defined, etc. So yes, you can do something here. Okay. Now, I want to go back to telling you now why our large deviation principles apply, but I think it's good that if we would make a break now. Yeah.
There should be some tea and sweets outside.
To do now, we're going to return to this collision local time of these two random walks. So remember that V was the number of times that the two walks meet. And we were interested in taking the expectation of Z to the V, either averaging over both walks or averaging over one walk and keeping the other walk fixed, and to then study when these expectations would explode, for what critical value Z1 and Z2 they would respectively explode. So in the next few slides I'm going to go through some calculation in which I'm going to prepare these two things into a shape that is ready to be used, where we can use these two large deviation principles. And I'm going to start by doing something very simple first. I'm going to write Z as Z minus 1 plus 1. Now that's not very difficult, and this is the kind of thing that you very often do. And then I'm having the V's power, so I'm going to expand this using the binomial formula. What is written here is just V choose n. And so I'm just using my binomial formula, and I'm beginning with the term 1, and then I'm having a sum from n is 1 up to V of Z minus 1 V choose n. Now, the interesting thing about this V choose n is because V is the number of self-intersections of the path, that this can be written as a big sum over all possible ordered choices of n times j1 up to jn. They have to be strictly different, they have to be positive, and I'm just then counting how often I'm requiring here the indicator that for once I fix these n times, that the two paths meet at the first time and they meet at the second time. And this big sum here simply is V choose n, because V is the sum of the indicator over all times where this is happening. And the choose n, the n factorial here, it comes because I'm ordering these terms here. And if I take this out, then this just becomes the product of this thing here, but with a decreasing number here. So this is a very simple step, which is just because V is the sum over all k of S is equal to S prime k. So now let's take expectations. I can take the expectation condition on S, or I can take the expectation conditioned on nothing of this thing, and I would end up with 1 plus this sum of powers of something which would be the expectation of this thing conditioned on X, and the expectation conditioned on nothing, where X for me now is the steps that the S walk makes. So the S is a walk that starts at the origin, that makes a number of RID steps, and the sequence of steps I call X. And then in this representation, when I take the expectation over S prime with fixed X, S, if I fix S, that's the same as fixing all the increments because my walk starts at the origin. And then what this should be is so this F1 should be, as it is here, the sum of over all the ordered J's of the probability of this event conditioned on knowing the entire path S, which is the same as knowing all the increments of the path S. And the other guy was just the expectation over S of this same thing. So if I take the expectation of this quantity, then I will get the F2.
What is that? Why is the V on the right side? V is random. V is the number in the previous.
Yeah. V is the intersection of collision of both, and I can ask what is its probability distribution over the joint law of S and S prime, or over the law of S prime when I fix S. That.
In the formula of the summation is going up to where?
Yeah, because let me see. Yeah, no. This is still a random variable. I'm sorry. Yeah, no, you're right. This should now be going up to infinity. I'm sorry. Yeah, no, this should go up to infinity. That's a typo. Thank you. Right. Right. Thank you. That's important. Okay. So I was interested in studying the blow-up critical values where these things start to become infinity, and I now have written everything in terms of some object and the expectation. This thing is the expectation of that object over X, and what that object is just you freeze the first walk S, and now you require that the other walk hits that walk at exactly the times J1 up to Jn, and then you may sum over all possible outcomes of the J1 to Jn, because you're saying I didn't care when these collisions were going up. This is basically the probability condition on X that I will have at least n self-intersections. Okay, so we need to study this object here. And now we can see how we could use this idea of the letters and the words. I'm thinking of this as a letter sequence. This is a sequence of ID steps that the random walk makes using its transition kernel. And so this now, the steps of the walk S, I can think of as a sequence of letters where the alphabet is just the d-dimensional integer lattice. So I can do that. I can think of the increments of my walk as generating an infinite letter sequence, which are just the sequence of steps. So I'm going to think of this as a sequence of letters, even though it originally was a sequence of steps. And I'm saying if I know all these steps, then what is the probability that the other walk manages to create n self-intersections? That's what we're trying to compute here. And I claim that comes out of a large deviation principle, because I'm going to think of the other walk as trying to sort of hit the other walk and make these self-intersections. So how does that go? I'm going to go through some computation in which I'm going to argue that this object that I'm interested in actually is some expectation with respect to the empirical process as we've seen it before, with respect to some function that I will give to you on the next slide. So I'm claiming that this object has something to do with the empirical process as we've seen it before. And I do this in the following way. I said, what is this? You wanted me to find the probability that given I freeze one work, that the other work exactly hits at these times. Well, let's write that down. There's still the sum that is in front of everything. And I say, you want to hit this walk, for instance, at time 1. Well, then your second walk must move in a time j1 minus j0, and I call j0, 0. That's the... In that time, it must move to the point that my random walk has reached at time 1. And that point is just the sum over k running from 1 up to j1 of xk. And then you must do that again. So now, over the next time interval, which runs from from j1 to minus j2, over that time interval, you must now make a further displacement, that you must make the same displacement that the other walk does in the next time interval. So each time you say, what is my random walk doing? You want me to intersect after a particular time. Well, then I have to make sure that I'm at that site of the other random walk at the same time. And that's what I do. So I can simply write this out in terms of a long sum and a product of transition kernels of one of the free random walk over something that depends on a frozen sequence. Now I'm going to do a little trick. I'm going to bring in the product of the rows, and I'm going to divide by the product of rows. So I'm doing something that will be useful later. I'm bringing in something and I'm correcting for it here. So I'm writing this product as the exponential of a logarithm, and then I put this in front and I have to correct for it here. Okay, and now I'm going to say, but if I look at this thing here, then this is exactly the law of my renewals, because every renewal had a probability distribution rho. So this thing here is the probability that my free random walk is exactly, my free loops here are exactly cutting out these intervals, and they're doing that with this probability. So this is the probability to see n renewals of length given by the increments of this sequence. And this whole stuff over here, I claim, can be written as a function of the ith word that I see in this program here. Remember, the increments are now my steps of my frozen random walk. These are the time lapses. And I'm saying this kernel depends on the time lapses, because the time lapses are here and they are there. And they depend on all the letters that I see in the time lapse. And that's exactly something that is the letters in a word. So I claim this whole thing is some function of what the ith word is, and the ith word for us is a word that has a length ji minus ji minus 1, and it sees as letters the letters x j minus 1 plus 1 all the way up to x ji. So what you see on the right hand side here is just a functional of the ith word. When I interpret this with the steps as the alphabet. And therefore, and I will tell you in a second what this is, well, let me go and do that. It is just this function. If you pick an n and you pick any steps that take values in your lattice, and for me my alphabet is now the lattice, then this function is just given by the probability that in n steps I move a distance x1 up to xn, summed out, divided by rho n. So this is a function that for every word and every of every length and every content will express my function in terms of the transition kernel over n steps of my random walk, plus the row that I've chosen. So that's good news. So this step was easy, and now I'm still conditioning on x, because x is always frozen. And now I look at this and say, aha, that's nice. This is a sum of from I to 1 up to n of the logarithm of a function of my ith word. But then I claim that this is a function of my empirical distribution of words, because if I divide by n, I can put the n up here, and then I could say, if you tell me how often I see, if I know the empirical distribution of the words, which I get from the empirical process by only looking at the first word, and this pi1 means take your whole empirical process and only look at the first word of your empirical process, then this is some probability distribution on the space of words, and I claim if this function log fi is averaged with respect to that empirical distribution, then that is literally the same as this object here, because this only looks at the ith word. And remember that this thing was defined already by randomizing over the words. So if I sum over all the words and I divide by n, then I'm exactly just looking at the empirical distribution of the words. And if I take the empirical process of the words, and I just look at the first word, I just get the empirical distribution of the words. So we've come a long way. It looked a little bit complicated, but this object that is the key in understand that's this object, and that's the key that we need to understand, can be written in terms of an exponential, and this exponential is the expectation over the random walk s prime, because the random walk s is fixed, and if we fix s or its increments, that's the same thing, and I'm supposed to take an expectation over some function with respect to this empirical process. So if you look at this, you say, well, if you would have an LDP for this process, and we do, then we should be able to say something about the asymptotics of this integral. Right, so now that's what we're going to do. Okay, let me remind you a bit that because this was the expectation of the f1, it's the same thing as the same quantity but not conditioning on x. So what is written here is the same thing as here, but then without the x. And for this quantity, we should be using the quenched LDP, and for this quantity, we should be using the annealed LDP. Now I'm still having this function, and I'm going to make a choice now. I'm deciding that the row n will be Pn00 divided by G00 minus 1. So this is, you can very easily see that this is the normalization constant for that, because the G00 is just the sum over this over all n including 0, and my row was supposed to live only on the positive length. So I'm picking this now as a row. The theory that I had before was perfectly valid for any row, and I say, let me now pick in this problem this particular row. If I do that, then I get something nice, because this is a finite number, because the random walk is transient. And if I forget about this finite number, I divide this by Pn00. Now the probability for a symmetric random walk to go in n steps from 0 to any point is always less than or equal than the probability to go to the origin. Okay, I need to worry about parity. This is only non-zero when n is even, and I should make sure that this is also having the right parity. And in fact, if you look at the original paper, I would have to look at times 2n, but I sort of simplified that a little bit, because that's no issue. then what happens is that this f becomes a bounded function. And that's nice because it's certainly a continuous function. If I change this very, very far out, the transition kernel doesn't change by much if you make a change very far out. So this function f is bounded and continuous. That's good news because these quantities here and this quantity here is begging for the use of Varadhan's lemma, because I have an LDP for this one and I have an LDP for the other one, and I'm having a bounded function, so that's good news. So we can go ahead. Little remark, it's log f, not f. So this function is continuous, it's bounded from above, but it may not be bounded from below. Now actually, it being not bounded from below is not a big problem, because if this becomes very negative, it's not really going to contribute to this integral. But there is a little thing that you have to do to cut, and then say you can apply Varadhan's lemma, and then show that the cut doesn't make any difference, and that's really very trivial, because if this becomes very negative, this is not going to make any contribution here. So what do we end up with? I'm ending up with, remember that I had these formulas. So my large deviation principle and Varadhan's lemma will tell me how fast exponentially this grows in n. So this will be growing like e to the n times something. Now that should allow me exactly to determine where these sums are going to blow up, right? Because this is z minus 1. So if this grows like e to the constant times n, and the e to the constant is bigger than 1 over z minus 1, then it blows up. And if it's smaller, it doesn't blow up. So by knowing the asymptotics of this thing, I'll be able to say what the critical values are. So that is the next thing that I'm going to do. I'm going to say, well, let me call r, let me call z equal to e to the r. So z is e to the r minus plus 1. Then z minus 1 is e to the r. And then the changeover should be happening. Am I taking the right sign? It's somewhere on the next page. Yeah, I'm taking zi is 1 plus e to the ri, and then zi minus 1 is e to the ri, and therefore I'll be able to exactly say that the r should be, the blow up happens when the r is exactly the growth rate as we get it out of Varadhan's lemma. So in the end, using Varadhan's lemma, we are ending up with two variational formulas. One is take the supremum over all q in the space of stationary probability distributions on infinite sequence of words, take the one word marginal of that and integrate your function log fi with respect to that law on words, and substitute the subtract the rate function as we found it for the Quenched model, which was this relative entropy and that specific relative entropy, and that supremum must be the point where you blow up. Similarly, in the other quantity where you say this thing is actually the expectation of that thing, so where I do not condition on x, I have this exact same formula. The only thing is that in the variational formula this term is not present, because this has only the annealed rate function, whereas the quenched rate function had the annealed rate function plus something else. So I have two variational formulas. They involve a one-word marginal of my process q, an integral with respect to some function, and then subtracting these two objects, and I'm supposed to take the supremum of these two. Okay. And I know that this number will be almost surely constant for every x, but here is the formula. Okay, so at this point, you look at these formulas and you say to yourself, well, that doesn't look so easy. I mean, this is a supremum over a very big space. This you have to take a marginal, you have to integrate over all possible words of some function. That is not so easy. It depends on your transition kernel, where you have to substitute this into there. Yeah, and then you have specific relative entropies, you have to subtract, and you have to find the maximum. So there is no way in which we will be able to compute this. But there is good news. We already knew that R1 and R2 are ordered. We knew that R1 could never be bigger than R2. Well, that's obvious, because here this variational formula is like that, but it has an extra term to make it smaller. So the fact that, so apparently, if I want to prove that there is a gap, all that I have to do is to show that this thing here is really significant and that it brings down the supremum. Now, that calculation is doable because there is something wonderful happening. This variational formula is solvable. Believe it or not, it's solvable. And the reason is the following. This only depends on the one word marginal of this distribution. If I want to minimize the relative entropy over stationary distributions of which I fix the 1 point marginal, so I'm saying I want the one word distribution to be given, but you may be dependent in any possible way you like, provided your one word has a certain distribution. Then over all possible choices of such Q's, the relative entropy is minimal when you take Q to be a product measure, because the relative entropy is with respect to a product measure. So there is something important coming from ergodic theory. The relative entropy of anything compared to a product measure, given that this anything has a one-word measure, is uniquely realized by simply taking for this process the product of the one-point measures. So the relative entropy of something compared to a product measure gets as small as possible when the something is also having a product measure. And that's something coming from convexity properties. So this supremum must be taken by a product Q, because this only depends on the 1 point marginal, and this is minimal by making Q a product. So this variational formula over sequences reduces to a variational formula over a single word. And so this whole thing is equal to the supremum over all distributions over a single word of the integral of the distribution of that single word log fi minus the relative entropy of that single word with respect to a single Q. And that's the fact that it's that reduction is something coming from ergodic theory. If your relative entropy is with respect to a product measure, you like to be as product as you can. And since this is only depending on the marginal, I can reduce this problem to a single word variational problem. And that single variational word problem is very easy to solve. That's just using Lagrange multipliers. And actually what you find is that the second variational formula has a unique maximizer. This unique maximizer is a product measure. And this product measure can be written down completely explicitly in terms of the kernel. It is this thing which we recognize from the F, and here are just independent letters. So basically what you do is you say you tell the random walk to make case n steps, and then this is weighted by looking at this probability kernel, which is the probability that another random walk ends up at the end catching up with you. And there's a certain normalizing factor. And now something wonderful is happening, because I know that this variational formula has a unique maximizer, which is taken at q equal to q bar to the power n. Now this has an extra term, so I claim if it is the case that for that particular q, that is the unique maximizer here, this term is non-zero, then I must have a gap. Because this can never be bigger than that one. This, I know what it is. It reaches its value at q being the product of q bar. So if at that particular value this term is non-zero, it must be then the case that R1 is less than R2. And so all that I have to check is that the psi that I get by taking this measure and doing the concatenation projection makes me end up with a measure that is not the measure nu, that's not the product measure as we have it, which was the law of the increments. And there was a lot of other little thing. You say, well, yeah, but your formula was also okay. It required that this has a finite mean, etc., etc. Because if this is different, then this relative entropy here is non-zero. This is only zero when this would be equal to that. So if its difference is non-zero, this is a positive number, and that's a number that's at least 1. So then I have a gap. And it's a very simple calculation. Remember that this is just the kernel itself, the one-step kernel. It's a very simple thing to do this computation. Well, it's very clear, first of all, that this is not the product measure, because this here is the product measure nu for the n steps, because remember that the increments were chosen according to the kernel. So the fact that there is this term here tells you that this is not equal to q. Q bar is not equal to q. Q would be this thing, but q bar is this thing times that, and that's not the same thing. Therefore this measure is not the same as that. Therefore the projection is not equal to that. And the conclusion is, as long as this is finite, I can use my formulas and I would get a gap. And it's a very trite computation to show that this word distribution has a finite length if and only if this sum is finite. And so the conclusion would be, if this is happening, then there is a gap. And that was the theorem that I wanted to prove. Okay, so I went through the trouble of saying these subsequent collisions that these random walks make can be seen as one walk makes a number of increments. I think of this as letters. After a certain well-prescribed time, the other walk has to also catch up with that and therefore also make the same increments. I then recognized that the quantities that I was interested in could be written in terms of the empirical process that we had been studying. Then I was applying Variation's lemma. This was giving me the blow-up points, and then I was having these, very complicated looking formulas, but the only thing that was important is that this formula could be solved because it has as a unique solution a product measure, and then I could show that at that project measure this term is really different because the projection of this solution here is not that, and therefore this is non-zero, and therefore there must be a gap between the two, and I'm done. And the only thing that was necessary was that I needed a finite length, and that will require me to have this condition. And what remains open is to show what happens when you don't have this condition. Actually, we believe that in the end this n would not be necessary, and there is some progress. So I'll give you some papers here. So this is the paper where we talk about this LDP at the ICM in Hyderabad. I explained, I had an invited talk where I was explaining why that thing is key to phase transitions of a couple of interesting systems, as I very briefly mentioned. So if you want to know more about that, you can look in the ICM proceedings. Then there were 4 papers in which there has been an attempt to remove this n, and it uses a completely different method. It goes by all sorts of estimates. It doesn't actually try to get expressions for these things, but now for some random walks that are transient but not strongly transient, this has been solved in a series of papers by Matthias and Noam Berger and Fabio Toninelli and Rongfeng Sun. So these 3 papers here's another paper in which we also got more into the details of these other applications. And they have results now that when you are, for instance, 3 or 4 dimensional, your random walk has certain isotropies and it satisfies certain moments, then they can also prove that the gap is there. But they don't get sort of any formulas for it. It's some kind of brute force, very clever and interesting computation of showing that they are different. Okay, so that is where the story stops, and it's an interesting application of a large deviation principle in a random environment, and again I want to emphasize this gap is the key to a number of phase transitions, all of which have some kind of random walk representation under them. And this has to do with polymers wanting to stick to an interface, or diffusions that are interacting with each other, or branching processes that branch and particles migrate. And you have questions like, does the population survive or not? Questions like, does the polymer stick to the interface or not? Or when you talk about interaction diffusions, is there an equilibrium or is there not an equilibrium? And then the presence of this gap will tell you that if you introduce certain, that depending on certain parameters, this you can have changes over between different types of phases. Okay, so I'll stop here. Thank you very much for your attention. Yeah.
When you prove that R2 is greater than R1,
Yeah.
you said it's enough to look at R1 just for Q bar.
Yeah.
Even though it was a supremum, why only at Q bar?
Okay, so the point here is that this frightening variational problem can be solved. Okay, that's a point, because here you only look at one point marginal, and this somehow wants to be as small as possible by making it a product measure. So this is taken at all product measures whose marginal is something. So then you can put the something here, this becomes a something, and you get a much simpler variational formula which you can solve by hand, and if you go through the computation you find this. So now I know that this is uniquely, I know the value of this thing, and it's taken at that particular measure. And now I claim that if this is already, okay, so this can never be bigger than that because there is this extra term. But if when this reaches its maximum, this is still something non-negative, then this can never stick its head out, this can never reach that, right? Because I know that everywhere else, this can never be bigger than that. Okay, but I agree, there is a little argument that you have to do, because you have to prove that that this would actually be sort of taking its value in a complex set. But it's really very simple, because I agree, I see your point now. We're living in an infinite dimensional space, so you have to be a bit careful. It's not that this could be sort of sliding mass away and then sort of mimicking that. So there is a little argument to be done, which actually uses compact level sets. Good point.
The uniqueness in the second one is also important, right?
Yeah, it's if I would not have this, I wouldn't know how to proceed. Because then you would say, I don't know where this is taken, and it could be that this is taken to something where this actually becomes very small, because or maybe there would be a maximizing sequence where this could be going to 0, and it's good fortune that you can compute this, and that's because annealed models are very easy. And then when you stick this in, you say, aha, I really get something different. So that's good fortune. Otherwise, so you're lucky here that you have formulas to play with. And when you wouldn't have this, it all gets much more cumbersome.
I have
Yeah,
concerns. I think maybe I'm missing something.
yeah,
One statement you made at the beginning of today's lectures.
yeah,
That, large deviations happens because
yeah,
if a rare event happens, it goes through the least likely of the unlikely.
Yeah. yeah, exactly.
I think we saw one instance of that in the Monday's lecture when you said that tau empty square is greater than tau full square.
Yeah, I mean, yeah,
Then that it has to go through a particular sequence of configurations is 1.
yeah, exactly. And this is always, so if you're, I mean, in good situations where you apply large deviation theory, you say, you ask me to do something, to do a particular large deviation, and I'm going to realize this in one specific way, and that is, of all the possible ways I could do it, the most likely way. So when I was talking about you have to go from an empty box to a full box, and you will pass through a certain configuration or set of configurations that are very close to a critical droplet, that is telling you there are a zillion other ways in which you could do it, but this is the least unlikely of all the unlikely ways. It is difficult to do, so you have to, so it tries this for many times because it's so unlikely, but eventually you will succeed.
But once you know that the
Yeah.
rare event has happened, that
Yeah.
becomes the sort of more or less the unique way, or rather which probability
Yeah,
one.
exactly. So, for instance, you could ask, you could say, I want to have a large deviation. What does the process look like when it does this large deviation? And then very often it has a nice structure. So let me give you a very example. You start with a fair coin. You throw it many times. Now I say, let's look at the event where approximately 75% of the time the coin came up heads. That's very unlikely, but suppose you do that. And I say, what does your sequence of coins tosses look like? The answer is, it looks like what happens when you take a 75% coin and you just throw with the 75% coin. So the statement is, there are a zillion ways in which I could create 75% of heads, but the way I will do it is as if I behave like a coin that has 75% success rather than 50% of success.
Yeah, but in many of the things
Yeah.
which we have been doing in the second part of the
Yeah.
lectures, is that only the exponential dominant term in the decay is captured.
Exactly.
So there could be lower order terms.
Absolutely. Yeah.
So is there an easy way of seeing that in these things also what that general principle actually does work?
Yeah, and so for instance, if your process is nice, then you can be more precise. So for instance, in the 75% coin case, you could ask, what are the fluctuations around the large deviation thing? So you could say, if I condition my process on having 75% of heads, what are the fluctuations? And it turns out that they are just the fluctuations of the 75% coin.
So that would turn on that will be context specific.
Yeah, so you could be, so the statement is even more precise. Even including the fluctuations, it will be just behaving like a 75% coin. Now that you need to do a computation to do that, but that is what is happening. And in the examples that I've been talking, they're all much more complicated problems where large deviations apply, but this same idea is there. This, for instance, the solution of this problem is a product measure, and it so happens that if you want to look at large deviations in an annealed setting, so if you say, I want to see some product measure, you will actually do this in the way that the variational formula prescribes. It will be the optimal value of something. So for instance, in my large deviation principle, you could say, well, what does the process actually do when it looks like something? Well, then I can tell you what the cost of that is, and I could say, what does the process do conditioned on doing something? And then very often it would be simply fluctuations of a typical process.
Likely path.
Yeah, exactly.
Can you say that has to happen with probability 1?
Very often, yeah. So here I could say, in this case, I could say in this problem here, I could say this blows up at a certain value, and it blows up because I see my two random walks doing something very particular, which is described by the solutions of these variational formulas. And for this variational formula, we have the solution. So I say, you will blow up exactly for that value, and then your random walk, you will be blowing up because your random walks are exactly doing what this Q bar measure is prescribing. And then you could say, conditioned on doing that, what more can you say about the random walks? That is a problem that I haven't thought about, but in principle, these are all things that you can do and that fit the same philosophy as the 75% coin.
Are there specific references which discuss your
it's a more difficult question.
I mean, let's say in a similar context of, let's say, in the Euclidean space.
Oh yeah, no. There are lots of things. For instance, there's an old theorem by Baudour and Rao. When you say you look at the empirical mean of in Kramer's theorem, can you describe the fluctuations around it? Yes, you can, and it is the fluctuations of a certain tilted process, and that will give you more precise estimates than the large deviation principles. So for simple examples like ID random variables or nice Gaussian processes or nice Markov processes, you can all do this in great detail. Once you go to more complicated processes, it may not be so obvious. It may be that you can guess what it should be doing, but that you have mathematically some problems to actually prove this, because you have to deal with conditional probabilities, and it may not be so easy. But there are lots of examples for which this is known. So there's some of the work in Dolske-Waardan, there's some work in the work of Erwin Bolthausen. Dembo Zetuni have done a number of things where you would see this coming out. I did with Andreas Greven a few things, and it's not so easy. It's a bit like saying if you have an LDP, then there should always be a CLT. In many cases, I would guess that what you were saying should be true, but there might be cases where I say, technically it's sort of difficult to push it out. But it should be very general.
Of course, if you know a priori that the decay has to be exponential, then perhaps
okay, yeah, in some,
as in Kramer's theorem.
Yeah, exactly, right.
This is Frank's last talk. We should thank him for all the lectures.
Okay, thank you so much for your attention.
square.